Okay, we're starting with our last unit, and we start first with chapter number 30, quantum physics. And the first slide will be a small one, and we will talk about photons. All right. Okay, photons. Photons are actually electromagnetic waves. Yeah, and photons is actually just light. Okay, so let's see, what is a photon? How can we calculate the energy of a photon? And you will see actually a formula that is very recognizable. And be able how we can calculate how many photons are emitted by a light source every second. All right. Okay, let's look at the electromagnetic spectrum, and then we see the visible light between 400 and 700 nanometers. Yeah, if we compare it with the other electromagnetic spectra. And by the way, don't forget that you need to know more or less the wavelength and the order of the wavelengths from longer wavelengths to smaller wavelengths. Okay? And especially when we come in this region, we also will discuss actually which one has more energy. Okay? And where does it depend on? All right. So for every slide, make some notes if you want to, and then I keep continuing. Just pause the video, alright? Alright. If you want to memorize this, the order rabbits made in a very unusual X-rated gardens. Radio waves, microwaves, infrared, and then we get the visible, then we get the ultraviolet, X-rays, and then the gamma rays. Yeah? Highest energy, highest frequency, what is the relation? More energy when the frequency increases. Okay? Now, don't forget that for all the electromagnetic wave, the speed is the speed of light, 3 times 10 to the power of 8 meters per second. Okay, if you want to mimic, pause the video and make some notes. I will put on the slideshow anyway later this week. Well, the wave equation we know already, that is the speed of the wave equals to the frequency times the wavelength. Yeah, and we know that the speed of light is 3 times 10 to the power of 8 meters per second in a vacuum. Okay? And this is for all electromagnetic waves. So we write this equation as C, speed of light, times the frequency times lambda. Okay? Alright, we move on. Maybe I'll show you this one later, but first I want to move on. And we are going to talk about the energy of a photon. Now, there's one thing that is interesting. Someone was asking me this in year 10. I think it was year 10 or 11. Which particle does not have a mass? It's a particle that does have no mass. No mass. Photon has no mass. Okay? Alright. So we can use the energy, the work out of the energy of an incoming photon, and we use this equation. And this equation might be already familiar to you because we use it also for the X-rays. Okay? Yeah. All right. Now, E is the energy of the photon in joules, F is the frequency of the radiation in hertz, and H, yes, there it is, That is the Planck's constant, 6 times 6, 3 times 10 to the negative 44. And now you see already that the higher the frequency, the higher the energy of the photon. Okay? So, photon of the energy is Planck's constant times the frequency of the radiation. Okay? Make a small note, pause the video, and I move on. Yeah. So, when we look in the visible light, we know that blue light has a higher frequency than red or orange, yeah, meaning it has more energy. And for some of you who are doing chemistry, you know when we actually move out of the visible light, we come into the region of the ultraviolet, and we can actually use ultraviolet light to break bonds. Okay? Alright. So, we have now two equations, and we can rearrange the equation by substituting the wave equation. F is c over lambda, so we get an equation, and I think we did this already in one of those questions. The energy is the Planck's constant times the speed of light divided by the wavelength. Okay? So the energy of a photon equals the Planck's constant, joules per second, times the speed of light, meters per second, in the wavelength of radiation in meter. Alright. Make some notes, and we move on. Question before you just answer this question. What is the energy of a photon? Calculate it, pause the video, and we move on. Lambda is given 400 nanometers, so that is 400 times 10 to the negative 9 meters. What is the energy? We don't know. We know the Planck's constant. We know that the speed of light is 3 times 10 to the power of 8 meters per second. So we can calculate the energy of a photon. Okay? Which is hc over lambda, and you should have calculated an energy of 4.97 times 10 to the negative 19 joules. Okay? Alright. What do we know about a laser? We're not really discussing that too much in A level, but it's at least nice how a laser more or less works, not the apparatus itself. It's a little bit complicated. We know that the light of a laser is very intense. It should be in phase. So that means we have a lot of light waves coming together, and they are in phase, yeah? Meaning they also need to have the same frequency. That's why we have blue or specific red lasers. You might remember when we used the diffraction grating last year, we were using the laser with a specific frequency. So that is monochromatic, means same frequency. Yeah? Each photon has the same frequency and energy. If we would call the number of photons leaving the lasers per second, and we could call them n, then we can actually calculate the energy emitted per second, which is actually the power of the beam is the amount of photons times the Planck's constant times the frequency of the light. Right? Pause video, make some notes. Alright. Question. We have a 5 milliwatt laser pointer emits a beam of red light of wavelength 670 nanometers. How many photons are emitted per second? Watt energy per second, so we can use that. The power is 5 times 10 to the negative 3 watt. Lambda is 670 times 10 to the negative 9 meters. And that is the amount of photons that we have to calculate. So we use this formula easily, yeah. N times H times C over N, yeah. And then we fill it in, and then it is 1.68 times 10 to the negative, to the power of 16 photons, yeah. You understand why we use power here? Because we asked for the photons that were emitted per second. Okay? And that's it for today. Tomorrow I will make 2 videos, and just to remind you, we will discuss the photoelectric effects. We have discussed that actually already a little bit. We will discuss the wave-particle duality. Light can behave as waves and as particles, as actually we see now, yeah, because we have calculated the energy of a photon. So actually we have calculated the energy of a particle. But photon is nothing else than light. Okay? Then we just explain a little bit about the origin of line of spectra. And for the guys who have been doing chemistry, they already should know more about that. Okay? Alright. That's it for today. Thank you for watching.